Linear programming is a process used to optimize an objective function based on certain constraints. In our example problem, we have 3 constraints. And those 3 constraints together make up a system of linear inequalities. So step 1 is to find the possible solutions to this system of inequalities. To find the possible solutions, we're going to graph each inequality. Our first inequality is y is greater than 2. Well, y equaling 2 is a horizontal line, so I'm going to start by first graphing a horizontal line through the point where y equals 2. I'm going to connect all of the points where y equals 2 with a solid line because it's or equals 2. And then I need to figure out where to shade based on this line. So I'm going to test the point 0, 0. 0, 0 is not on the line, so I can test it. Plug in 0 for y. Is 0 greater than 2? The answer is no. So I want to shade to not include 0, 0. So I'm going to shade above this line. My second constraint is the line x is greater than or equal to 0. Well, x equals 0 is a vertical line, so I'm going to start by graphing a vertical line through the point where all the points where x equals 0. Now I need to test a point not on the line. Well, 0, 0 is on the line, so I'm going to test a point not on the line. I can pick any point, but this point right here will be easy to test. 1, 0. So I'm going to test the point 1, 0 in this inequality. So I'm going to plug 1 in for x, and I end up with a true statement. So I want to shade to include the point 1, 0. So I'm going to shade to the right of this line. And my last inequality is this. X plus 3y has to be less than or equal to 15. To graph this inequality, I'm going to first solve for y. Negative 1/3 x plus 5. Up 1, 2, 3, 4, 5. And from there I have a slope of negative 1/3. And again, I want to test a point not on this line, so I'm going to test the point 0, 0. When I plug 0 in for x and 0 in for y, I end up with y is less than or equal to 5. and that is a true inequality, so I want to shade to include 0, 0. Now if you look at my graph, I have a whole bunch of points, or I have my entire graph shaded. The region that I'm concerned with is the region where all of the shades intersect. The region where all of the shades intersect is this triangle right here. From this point down to this point, across to this point, and then diagonally to here. So I'm going to shade in that region nice and dark. This triangle is called my feasible region. The reason it's my feasible region, it's all the ordered pairs that make this system of inequalities true. And in this case, I have a bounded feasible region. It means that I have a feasible region that's closed. My other regions in this graph are unbounded. This triangle is bounded. So I've done step 1 of my linear programming process. I've graphed my system of linear equalities to come up with the feasible region. Step 2 is to optimize that feasible region. I need to find the maximum and minimum outputs of the objective function. I'm not finding the maximum and minimum values in my feasible region. I'm going to take those points and plug them into an objective function to maximize and minimize this function. So it's not necessarily the highest or the lowest point in my feasible region. It's what happens to those points when I plug them into the objective function. The highest and lowest points are going to always occur at the vertices of my feasible region. So those are the points that I'm going to test. So I'm going to test the vertices of my feasible region. In this case, I have a triangle, so I have 3 vertices. I have a vertex right here, and right here, and right here. So I need to use the ordered pairs for those 3 vertices. My first vertex is at the ordered pair 0, 2. My second vertex is at the ordered pair 0, 3. And my third vertex is at the ordered pair 9, 2. Now since all of these inequalities are or equal to, all of these points that are on the region are possible solutions. So I'm going to test these 3 points. To test them, I'm going to plug them into this objective function. I'm going to plug 0 in for x and 2 in for y, and I end up with 8. And I'm going to plug 0 in for x and 3 in for y, and I end up with 12. And then I'm going to plug in 9 for x and 2 in for y, and I end up with 26. So the values that I'm concerned with, that I'm trying to optimize, maximize, and minimize, are these outputs right here after I've plugged in my vertices. So my lowest output is this 8. So I have a minimum of 8 at the ordered pair 0, 2. And I have a maximum of 26 at the ordered pair 9, 2. So this is ultimately my final answer.